Hi everyone. I have lots of interesting information to share with you today, and a lot of it isn't displayed here on the map. We're going to go over this stuff as well, and I'll talk a little bit about the stuff that isn't shown first. So I'm going to share with you a tool that I had to design my very first series of capacitor testers. And this tool allows me to measure voltages at extremely small currents. And that will be shown here. Now, the new capacitor tester is still being built, and I have some parts on order for the new probe that I'm designing for it, and I'm going to share that with you as well. It's a pretty special tool that you'll see here in just a little bit. So I've never displayed this tool before or even talked about this stuff, and I'm also going to share with you the original specs for the original capacitor testers. I'll show you what was needed in order to do calibration and the design of these devices. And we're going to also talk about cleaning band switches. So big wafer switches like this. This is used in a transmitter application, but the same thing goes for smaller things. We'll talk about cleaning relays and switches, toggle switches and things like that. There's a few little tricks that you may not know about in toggle switches, and I've had very good success with this process. So let's get started. Here's a large wafer switch that is out of a large broadcast transmitter. And the reason that I'm using this to display here and using this as the example is because this is just the bigger version of what you have. So say you have a Kenwood or an ICOM or a Heathkit or a Hammerland or a Yaesu, whatever you have that has a band switch inside it, it's going to be the smaller version of this. And they're put together pretty much the same way. This has got ceramic wafers inside it. A lot of them have a fibrous material wafer, and some of them have ceramic as well. So I'll talk about the differences and the cleaning precautions in both applications. So in an application like this, so this is a really, really big switch, and as you can see, these are a ceramic wafer. What I normally do to clean something like this is I'll hose the whole thing down in deoxit or that MG Chemical Super Contact Cleaner, the same stuff that I displayed in the previous video, and I'll show you the cans here in a little while again. Hose the whole thing down, and then I'll move this back and forth a whole bunch of times. Now this is a really, I guess you could say, big clicky switch. It's, lots and lots of force to move this really large chicken head knob here is just slipping on the shaft, but it gives you the idea at any rate. So you can hose the whole thing down, and the thing with deoxit is I get a lot of questions is, does it swell the fibrous material? Well, I've never found it myself to do that, the deoxit, and I find that deoxit will eventually evaporate in actually quite a short period of time. Now here's the thing, it'll leave the switch working really well. And same with an MG Chemicals contact cleaner. The switch will work really well with just that. The problem is that I find they don't last very long. So it'll work good for, maybe a month or so. And then after that, the contacts and everything will start to tarnish up again and get dirty. And then of course you start dealing with an intermittent switch again. So as I used in the potentiometers, and that again is in the previous video, that WD-40 spray and stay, I will use that on these as well. So what I'll do is I'll spray that or put it onto a Q-tip and put it onto the contacts and in the center area. Now, if the switch is solid ceramic, so there's no fibrous, material in there, spraying the whole thing down with the spray and stay, I find is fine. Okay, now you don't want it dripping off because it is a light oil. You don't want it dripping off the contacts. And if you're dealing with, something that's going to be dealing with lots and lots of current, you got to be careful with that as well. So I'm talking about, switches that are in small transmitters and receivers and things like that. If you're in an industrial application and it's, switching incredible amounts of current, a lot of the times the contacts need to be dry. And in a case when contacts are dry, they spark anyways in high current applications, and they're self-cleaning, and that's how relays self-clean themselves, and I'll talk a little bit more about that. So again, common sense has to be used in this, and of course use this information at your own risk. Okay, so this is just what I found that works for me, and for me it works very well. Now, if this whole thing was a fibrous wafer switch, and there are lots of them out there, and in fact, I've opened up so many Yaesus and Kenwoods and things like that, and you look at the actual switch that switches all, the band switching, the oscillator section, and the tank circuit and that, and they're soaked People have been in there and they've soaked them with contact cleaner. And the problem with that is if you use a contact cleaner that won't evaporate, a lot of the times I find that it does make the fibrous material soft. Now, I haven't found that it swells it so much as it just makes it soft and they break easier. Okay, so what you want to do in a case like that is you can hose the thing down with deoxit. That's fine. I find there's no problems with that because it'll end up drying up and you end up with, a dry switch like this. When it comes to stopping the contacts from oxidizing, this is where you have to use a Q-tip, something like this. And I would put spray and stay on this, and I would go over the actual contacts, not getting it on the fibrous material. As little as possible. Of course, a lot of the times there's a fibrous disc holding the contacts in the center. You can't avoid that, but you want as little on the actual discs as possible. Now, a lot of people get confused. They think that, I've hosed down the whole switch and it's not drying up. Well, chances are somebody before you has sprayed some contact cleaner on it that has a light oil in it, and you're just noticing it. All right, so chances are the switch was probably soaked with an oily compound before. I find that deoxit will leave things just dry, and it does it with, the toggle switches that I've, cleaned. And that's another thing I will talk about here. I'll show you some tricks with some toggle switches in a little bit. At any rate, I find that it leaves everything just dry. So, and that's fine because that's what you want. So you want the whole thing to be dried up. In a case like this where you can take it apart, of course, that is, again, a definite bonus. You would want to do that in a case like this. Snap a picture of this with your phone or with a camera of some sort. And of course, you would want lines marking everything. So put a felt line on everything. So when you take the whole thing apart, it goes back the same way. Mark the front side of the switch and the back side of the switch, which is to the back. And sometimes you even want to mark these spacers because some of them are different sizes. So you have to be careful with the spacers as well. So don't be afraid of marking things, because if it's a band switch, it's going to be inside something. If you use a marker that isn't too incredibly, I guess you could say, it won't last an incredibly long time, indelible markers, but if it won't last a long time, something that maybe rub off, you can clean it up relatively easy. If you use a lot of markers on this fibrous material, what'll end up happening is it'll go right into the fiber itself and you'll never get the marking off. So some things that you would want to keep in mind. Using that spray and stay in an area like this is very important because there's a ball that's going over. As you can see, it looks like little bumps here. And those little notches are what holds this in place. That's a thing that will wear, and same here with this area around the steel ball. You also want to get that kind of stuff in the shaft, but again, you want to be careful because you can see here there's a fibrous material. The actual center shaft is a fibrous material, and then there's a ceramic portion here. So this is designed for some very, very high voltage. So some things that you're going to want to keep in mind. So if the switch is fully ceramic and it's in some form of an application like a receiver, something like that, I find that using the spray and stay, I even have done this on my coax switches, the ceramic coax switches. The spray and stay, getting it on the actual, the entire ceramic area is fine. Things that need to be kept in mind is that if the actual switch is in an open area and there is an oily substance on it, dust will stick to it and it'll create more problems. So something to keep in mind. Again, this is why I kind of suggest for both applications, if you can, a lot of the times you can't just because of where they are in some of the transceivers and receivers. But if you can, use the Q-tip and then just get the spray and stay on the contacts themselves and the center area here of the wafer switch. You want to get it on that and keep it off as much fiber material as possible. Again, the oily substance will stop these from tarnishing again or oxidizing again for a very long period of time, and that's what's very important. Is when you spray these things and you move them around, so you've hosed the whole thing down in deoxit and you're moving the thing back and forth, right? And it's in a receiver. You're not necessarily holding it like I am, but it's in a receiver. And you're moving this thing back and forth like this. What you're doing is you're actually cleaning the area off with the contact. So you've hosed it down once, you move it back and forth a whole bunch of times, and then you have to spray it down again to get all of the grunge off that you've basically scraped off with the fingers here. and then do it again. You want to clean it out. So you want to do it a bunch of times. And then, of course, once this is completely dry, don't put the oily substance or spray and stay on when it's wet, because it's going to mix with it, and then it'll never dry up. So wait till the whole thing dries up. And then after that, you want to take the spray and stay, and then just take a Q-tip and then coat the areas that are, making contact. As you can see, the contact area in these switches is very small. You can see that little polished area here. That's all that's making contact with the fingers here. That's it. So there isn't a whole lot of contact area, and this is the reason that in transmitters like the E.F. Johnson, Viking, Valiant, and the DX100s, the Heathkit DX100s and things like that, you'll find that these little contacts, they lose their temper. All right. Now, I'm not saying they're getting angry or nothing like that, but they're going to lose their temper to the point to where they're not going to, stay together. Now, these little fingers that you see in here, you can see that little finger down in there? You can see that when I move the switch, you can see how this wafer here or here comes through these two fingers and it separates them. So you can see there's a little bit of a bevel here, right? So that the sharp edge doesn't get jammed up on the switch. You see that right there? So I'll separate the contacts. See that? I'm separating the contacts with my screwdriver. Now there's a lot of spring tension here, and they snap back together again. See that? It'll come back together. That's how they're supposed to be. In transmitters like the E.F. Johnson, sometimes a Ranger, depending on how bad the load has been. So people, trying to load up their, old mattress outside in the yard or something like that as an antenna, what ends up happening is the contacts end up getting hot. Okay, and then they lose their spring tension. So what you have to do in a case like that is, once the thing's all cleaned and everything is ready to go, what you really want to do is open the switch to a point to where this, the center portion here is not making contact with it. All right, so you want this to be open so you can get at the actual fingers. So get everything out of the way. And then what you do is you push on the bottom and you lift the bottom up, and then you push on the top and you bring the top down. And a lot of the times that will close the fingers again, so they're nice and tight. Okay. Now that doesn't mean that they're going to stay like this, right? Because they've been hot, and a lot of the times they've lost their tension. So if they're open like this, so for example, okay, in the switch like this, okay, say that this one has lost its tension, so you want to pry up and push down, okay? So these fingers are like this, so you're going to want to pry up, so you're going to push the bottom portion up, and then you're going to push the top portion down so that it makes tension on that again. So now, this time, when that center piece comes running through, of course, it's going to separate them and go like this, right? All right, so you want to keep that in mind. Now, you're probably saying, well, that'll fix it for the short term. What will end up fixing it on the long term? Because they're going to end up separating again and staying separated. Well, a paper clip is your friend. So what you want to do with a paper clip, I just have a resistor here, and I've got it bent already. So just take a paper clip, all right, straighten it all out, and then put a bend in it like this, okay? So I'll find one of these ones that are open here. There it is. Now, you can see that there's a little bit of a divot in the cup here. Okay, so what I'll do is I'll just zoom on into this a little further. Okay, so you can see there's a bit of a divot in the cup here. Now, with this desoldered, there's a hole right here. Okay, so what you would do is you would take the paper clip and push it through, okay? And then what you would do is you would take that paper clip, and you see how I've got this right in that little divot area there? Put tension on this, lift this up, and then wrap the paper clip around here. And what it does is that puts down tension on the contact, and if you can, do it to the other side as well. And this will save the band switches. So you've basically added an external spring to take care of the spring tension that's no longer here anymore. So it just pushes down on it like so. So there's a little trick that I've learned over the years of fixing, I can't tell you how many countless numbers of damaged band switches. And again, a lot of this is done through ham operators, hot switching band switches, or just bad loads. This your, an antenna that's open, or a piece of bad feed line or something like that. And what ends up happening is somebody isn't watching their standing waves, or, looking at the reflected power. And what ends up happening is it ends up backing up, and it heats up these little things, and they just get soft. And then, of course, you hear hissing in your transmitter. What's that hissing? And if you're on, AM, amplitude modulation, doing something like that, a lot of the times the guy on the receiving end will see it in your signal, or hear it even. They'll hear the hissing of your band switch. All right, because you have an intermittent transmission. And what happens is the contact buzzes, between the actual finger and the plate it's making contact. So it's actually a little blue spark in there that's going hissing and sizzling away. And that's no good, because eventually what ends up happening is it'll eat a hole in either the finger or the contact switch. Now, this is really common in Johnson Viking Valiants and DX100s, Heathkit DX100s. And any type of large transmitter that has a small band switch in it, there's a lot of them out there that they put band switches in that do this. If you have any type of ham radio amplifier, a lot of the times the band switches in them go away too, and that's usually from somebody that's either been hot switching, so key down kind of thing, hot switch, which just arcs contacts out. Antenna tuners are another real sore spot for this. I had this antenna tuner that I bought at a ham swap meet, and this is one of those real bad purchases. So I paid a fair price for the thing, opened the thing up, and these were melted right off. Right here. Like, just melted off all over the place. And I'm like, wow. So this thing's going to be wired for a single band. And anyways, that was a really bad... It was a specific band switch, nothing that you could get replacement parts for. So, yeah, something that wasn't very easily replaced. This is one of my go-to boxes of toggle switches that I use in many of my projects. I'll just randomly grab one. So, you know what? Let's randomly grab this one because it's a little bit bigger. Now, lubricating these switches and cleaning them is actually quite simple. So I'll just zoom on in. Actually, I'll get this out of the way because it's going to be kind of glary. I'll zoom on into this. So lubricating these and cleaning these is actually really quite simple. You're probably saying to yourself, well, there's a little ball in there. How does it get beyond that? Well, in many of these switches, you can push it down. You see that? It actually moved down quite a ways. So again, deaux it down there. I fill it up, push it down, and then usually it runs down inside. And then I'll do it again a bunch of times to get lots of that in here. And then I'll move this back and forth. Many times. Very important. Do it again. A lot of the times you'll find that it's starting to weep out little areas on the bottom. Absolutely fine. And with the switches like this, so for example, in the capacitor tester, my ultra forecasting one, I used a bunch of switches out of the box. And, just due to low currents and things like that passing through the actual switch itself, it's kind of important to have very good contact all the time. And getting an intermittent contact with a switch like this is really quite common. So spraying deaux down there, would work again for a while. And then, of course, it would get intermittent. Spray some more and move it around a whole bunch, would get intermittent. Spray some in, move it around, put some of that spray and stay down there, push it down, and shoot some in there a bunch of times, move it back and forth a whole bunch of times, and never again has it ever been intermittent. So again, another example of how well that works. Cleaning relay contacts is actually very easy in a case like this. So when you have a relay that you can remove the case, you just pry the tangs up and then the plastic cover comes off. I'm sure you've all done this at some time. And then you just remove the spring and you can actually take the whole front area right out. Now, when you're dealing with contacts like this, usually relays of this size are used in an application where there's current being passed through the contacts. And relays self-clean their contacts as they spark. So if you have a big relay like this and it's not really passing any type of current, you're going to find that the connection in the relay will get intermittent after a while, whereas if it was sparking and passing current, it doesn't. Again, the actual sparking is a continual cleaning process in relays. Now, unfortunately, this cleaning process in the relays wears the contacts as it's doing it. Passing current does that. You'll find that a lot of small signal relays, and one of those would be right here, they're completely sealed up, and they're like this for a reason, so that everything inside is basically no atmosphere inside, and you need that to, keep the contacts clean. If there's any type of atmosphere or anything inside like that, what ends up happening is, contacts tarnish and, things happen. So this particular relay is designed for a really small signal. So, for example, moving a receive antenna around or something like that. This is where something like this is. Sometimes you find relays like this in the front end of oscilloscopes as well. Okay, but in a case like this, what you want to do, if the contacts are bad, you can usually take these things apart, and what I do is I try and polish them. All right, so if they're really badly pitted, sometimes you need to sand them, or you can use a burnishing tool, an actual relay burnishing type of tool, and you can clean them up like that. If you don't have to sand them, I would suggest not, because a lot of the times they're plated. The actual contact itself inside has a plating on it. And if you take the plating off, you'll find that the contacts will stick, or it just, they'll get intermittent again in a short period. So if you can polish them with a silver polish or any type of a metal polish, get in there and clean them up with a rag. Just spend lots of time polishing them. The contacts in the middle and the contacts on top as well. You're probably going to be better off. Let's see if I can open this thing up here and give you an idea of taking one of these things apart. A lot of the times you need 2 screwdrivers for this. And I got to be very careful that I do not stab myself with a screwdriver. So what I'm going to do is I'm going to put this one in this side, and I'm going to get another one and put it in this side, and that way it'll hold both sides open, and I can just slide that out. So where is another screwdriver of the same size? Right here. Okay. So I'm going to hold this one side open, just in case that wasn't in the shot, and I'm going to open this side here as well. This is the little lock on the side, so I got to be careful I don't stab myself here, because this happens with this. Okay, so now this will allow me just to pull the relay out past the little lock, and I can get this off. Now you got to be careful, because a lot of the times when you're doing that, it's very tight and it is very easy to slip off and then stab yourself with a screwdriver. So be very careful when you're doing that. Don't ask me how I know this over and over again. So at any rate, so here it is, it's open, and getting these things apart is really quite easy. Now, one of the things that needs to be noticed, I don't know if I can get in any closer with this lens, I can't. Another thing that needs to be taken into consideration is you can see we have the center of the relay here, which is the magnet, all right, and then we have the arm here, okay? So now you'll notice, watch the contacts on the bottom, okay? So watch this contact, you'll see it come into contact here, but watch, you'll still see a space between the actual electromagnet and the arm. So now it's already making contact. Look at all that space in there, right? I can still close it. See that? Lots of space. Now, don't be confused by this. There's a little piece of the core sticking out in there. So it's already making contact there, but there's still a gap. And you can see me closing that gap. So it's making contact there. You can see the rest of that. Now, you can see as it's doing that, it's putting tension on the contact. You don't want these just to lightly touch like this and then it's closed. If you have to retension these contacts, you want to make sure that these touch before the arm touches the electromagnet. So that way there's tension on it. And you'll also notice that it creates a scrubbing type of a motion on the contact to stop them from welding as well. All of these things were taken into consideration when they designed these relays. So if you watch this contact, you'll actually see it rub downwards. Okay? See how it's kind of rubbing downwards as it's making contact? That's to clean the contacts. All right, and it's the same kind of thing on this side. It's touching, but if I let it go, you see how it pulls up? So it has a scrubbing motion, and they're using that as well as, for tension reasons to make sure the contact is good. Now, getting something like this apart is relatively easy. Use eye protection as you're doing this, because a lot of the times these things will take off. Make sure it doesn't. All you do is you just unclip this spring like so, and on the top, this pulls out, and you can take the whole thing apart just like that. Here's a topic that really isn't talked about all that often, and really isn't very well understood by lots of technicians and even engineers. I've seen lots of mistakes being made with this, and it really is just a measurement error. So whenever you're measuring a very, very low current circuit, or, say a high impedance circuit, special measurement techniques need to be taken because the actual meter itself will load the circuit. Now, I've talked about this a lot with spectrum analyzers and things like that, but at standard DMM and even some of the most expensive DMMs, even the ones with the high impedance setting, will still be affected, and you need a special probe for this. Now, I'll give you an example of this here. So here I have a voltage divider, 3 voltage dividers. Okay, so I'll just take the negative here, put it onto the negative, and we'll go right to the source here. So we have about 30 volts. Okay, so there's 30 volts across these 2 resistors, these 2 resistors, and these 2 resistors. So these are creating dividers. So whenever you make a voltage divider, if you're making a divider, there should be around 15 in the middle. Now, it's not always the same because of inaccuracies in the resistors, and even small inaccuracies will affect the actual outcome. So, for example here, I have 2.4 k ohm resistors. Now, there's going to be quite a bit of current at the center here. So you can see that we're at 14.985. All right, so that's not exactly at 15 volts, even though we have 30 volts, right? Almost spot on here. And that's, of course, because of inaccuracies in the resistor. And this is why precision voltage dividers usually use 1% or lower resistors. And many of them are hand graded as well. And you'll see why here in a moment. Here's another little thing that you don't see very often. So you're working on a vacuum tube circuit and you see, say, 2 22 meg resistors, and both of those 22 meg resistors here are forming a voltage divider, and you're thinking, oh, okay, I'm going to test them. So I have, say, 30 volts at the top here, and I come to the center, and oh, look, there's 6 volts at the center. One of these resistors has got to be really far off, right? Well, no. What's happening here is the parallel resistance inside this meter right now in the DC setting is adding to this bottom resistor here, right? So I'm adding resistor. These 2 leads, as I'm putting it across here, is adding resistance across here. And because there's so low current across both of these resistors right now, it really affects the reading. So these here are 1 billion ohm resistors. So this is a 1 gig ohm resistor and a 1 gig ohm resistor. Okay, so if I go to the center of that, right, we know we have 15 volts or 30 volts at the top here, so we should have around 15 at the center, right? Well, obviously, definitely not with a meter like this. And even your extremely expensive Fluke 8845 that has the high impedance setting will not see this. Okay, and this is why you need a special probe for this. Now, when I was developing that capacitor tester, of course, I'm dealing with some extremely sensitive settings, and I'll talk about those specs here in just a little bit. So I had to design a probe for that, and I've never shown this probe before, but here it is. This is one of them. I have it all hooked up, so of course everything's going to be all tangled up as I'm showing you this. I'll just untangle the wires here. Give me a moment. There it is. This is the probe. Looks kind of like the Super Probe. It's a Heathkit probe shell again. So this runs off to the meter. All right, this is the tip. You can see how I have it grounded because this is extremely high impedance and I don't want to zap the IC inside that is doing this. So when you're using any type of a probe like this, you always should keep the tip grounded when not in use because, again, this is extremely high impedance here, and I'll open this up even for you. It's been a while. I'll open this thing up and I'll show you what's inside here in just a little bit, okay? So now, this probe here takes a separate power source. It needs to be powered, and that's in this XLR type cable right here. I just used an XLR cable, and this is just some of that standard Teflon coax I'm using to run out of here. Now, the build construction of something like this is very specific because, we're dealing with billions of ohms, all right? The IC itself is good to 10 to the 12, okay? So the input impedance of the IC itself is, get to about 1 trillion ohms, something like that. So very high impedance. So not very much parallel impedance there. Now, there's a lot of things that affects that still. You have leakage in the FR4 board. I have a filter network in the front of this that has a capacitor, so it will stop me from zapping that IC. So basically, if I hit this with a bit of static or something like that, it has to go through a resistor network, and it has to quickly charge a cap, so the cap absorbs the the zap a lot of the times, things like that. So, lots of thought went into this thing here. But this is for myself, and I'm developing another one for the next capacitor tester. I've been using this one up till now. So what I'm going to do here is I'm going to switch the leads out. So these are just standard, standard leads in this. So what I'll do is I'll take these are on my top meter right now. Get that out of here. And plug this into the bottom meter here. And I'll talk a little bit more about this in just a little while. Okay. Talk a little bit more about this and the selection of components and things like that. Okay, so I'm going to turn on the power supply for this. Now, I'm not going to share the design of this probe with you just for reasons that I'm taking the IC inside this well beyond where it's supposed to go. And this is because I've spent a lot of time grading ICs. And it's because I had what I had on hand and it worked very well. I have, as I mentioned earlier, I have a bunch of components on order and they should actually be here very soon. They're special components and that's going to go into the new probe, and they're 10 to the 13, the input impedance. So we're, dealing with, around 10 trillion ohms. So they're very little parallel resistance. Again, the leakage in the FR4 board and the IC package, maybe, who knows, even stuff like that, right? Is going to be there. So that's the input impedance is extremely high. So it's a little bit better than the device I got in here. Mind you, the device I have in here is very good. Okay, so I'll turn this on. And I got to turn the power supply over here. Okay. So with it grounded, you can see it's very close, to sitting. This is, of course, a hand-graded component. If I remove this, it's going to go all over the place, right? This is extremely sensitive. So what I'll do is I just clip this onto ground, so this whole ground rail is connected, so I can use this for all of this. Okay. So if I go here, 14.99 volts, very close to what it was before. It was 14.985 before, right? So you can even tell there's a little bit of loading from the meter there. Okay. Now, these resistors are not perfect, okay? So I just picked these out of the bin, so keep in mind it's going to be like before, right? So at the top here, I say we're dealing with 30 volts at the top, right? And almost 15 right here. So now if I touch the center of this, look at that, 15 volts. Whereas before we were at 6. Right? Now these are 1 billion ohm resistors. Now that's quite the divider at 30 volts. All right? So this here is, extremely low current in the nanoamps. All right? At this point here. So what I'm going to do is touch it right here. And look at that. Now the inaccuracy that you're seeing there is just the inaccuracy in the resistors. All right, right at the center. Now again, if I remove this, okay, we'll just short this out like so. That took a lot of time. Usually they'll sit off a little bit, so that did take quite a bit of time to do that. So, in the next design, I'll talk a little bit more about that. Look at this thing even sitting open. I get, one. Okay, so I'll put this here, and this here. When I build a device, especially when I'm developing something to release to all of you guys, I take a lot of time in just the device design itself. Now this will drift a little bit, of course. It will move around with temperature. You might see this, and of course this is going to drift as well. So dealing with them both, right? This was set up on a bunch of different meters, and I used a bunch of meters for comparison to each other. So again, we'll test this again, right? So here we go. And like 6 volts there, right? And then of course here, you get nothing, right? 0.3 of a volt. And then there's enough current here that, it's going to be okay. Right? Because these are 2.4K resistors across, 30 volts. There's definitely going to be some current there. So that is the difference between a probe that will be sensitive enough to take these measurements. Now, I know a lot of you have built this capacitor tester. You can actually see, well, it's actually going down. That's pretty good. It's creeping back down to zeros again. I don't expect it to stay there. So at any rate, a lot of you have tried to build this other, the forecasting capacitor tester, and you're having a lot of problems of making the thing work correctly. And in my videos, I explained that the way it needs to really be built with special flux and everything like that, because the sensitivity of that device is really quite extreme. And the one that's going to be released is going to be even more extreme. All right. So this will really test all of your building skills. So when you're building something like this, everything has to be taken, leakage in the FR4 board, leakage in the flux, leakage between traces, all sorts of things have to be taken in, especially when you're dealing with, the amounts of current that are going to be passed. Now, this is the reason that this thing had to be built, and the next one will be built as well. So again, we'll just show you this again, right? 14,990, right? And then again at the center, 15 volts, nice and quick. And then here, 15 volts, right at the center. So this is a 1 gig ohm divider. So this is at 2 gig ohms from this end to this end here. So 1 gig ohm right in the center. So that is why a tool like this is needed. And basically this is unity gain. All right, so this device does not provide anything because it needs to measure the same thing as the meter. We don't want any gain. If there's any gain inside the probe, we're going to get an incorrect reading, and we can't have that. Now, the probe is only good to what the IC can deal with, because when you're dealing with a split supply like this has, this is tailored to the top end, because I'm not reading negative voltages with this, okay? And it's the same thing with an op amp, okay? So inside this thing is an op amp, really, is what it is. And an older style op amp made by Motorola, and I'll show you this here in a little bit. Lots of time in grading. Oh man, I can't tell you how many of those things I went through just to get the, the readings and everything as good as they are. At any rate, the positive supply is what I'm concerned with on this op amp, because the positive supply is going to tell me how high I can read with this. Now, this is going to read to a maximum of about 32 volts. It'll be accurate to about 32. And the negative supply is -5. There's -5 volts on this. So the op amp has -5, and the positive supply to this is about 34. So it's exceeding the little op amp that I have in here. You'll see in a little bit, it's exceeding its supply voltage. But it's completely fine, and it had no issues. And as I say, I've spent lots of time grading and testing these things. So if I was to release the same type of op amp and the same design to you, there's a good chance that you would get an op amp that might not hold up to what this is doing. This is a pretty superior op amp inside this thing. The next one I will release. The next one will be able to read to a very close, well, depending on how I set it up, it can read almost to 100 volts positive, and then of course there would be the negative side as well, so almost. So if I set it up for a split supply, say 50 volts positive, 50 volts negative, something like that, you could get almost a 50 volts reading out of this thing. Now, the power supply in the capacitor tester itself is 29.5 max, right? So if you were to set it out a little bit, say it was 30 volts, this will go 2 volts above that threshold, and that's what I needed, and that's what this is designed to do. It'll actually, at the time when I was dealing with the batteries at first, it's quite a bit lower than that, so I didn't have to worry about it. So this is a very purpose-built device. So this is good to about 32 volts, something like that. This will read up to. And for most sensitive work at lower voltages, this is absolutely fine, this design here. But the newer one will go much, much higher. So anyways, there's an example of this. So what I'll do now is I'm going to get the capacitor tester, and I'll show you exactly how sensitive it really is. This is the Carlson low voltage leakage tester. This is the forecasting version that I released quite some time ago, and it's an incredibly useful tool. For those of you that have built this thing and are using it, you know how incredibly useful this is. It will forecast failures before they even happen in capacitors. And it's a wonderful feature for people that are, say, if you're a repairman or a technician dealing with people that are repairing guitar amplifiers for live performances, things like that, and you want to see if maybe something's going to fail while it's on stage, because it's nothing worse than that, right? So this thing here will detect issues before it happens and, of course, make you look like the real star, especially if you find a component that's on its way out. So many, many uses in this, and many of you have built this, many of you have built this with great success and shared your success stories and even some small videos showing you using this. So I'm glad all of you are enjoying this particular version of the capacitor tester. The next one is just about done. Now, there is an incredible amount of work. I can't even stress the word incredible amount of work that has gone into this next one here. And I've ordered up some more parts again, and hopefully they'll be here this weekend, and I will be able to continue on working with that one. It should be released very shortly. I was hoping to have it released actually now, but there's some things that I'm still improving on. I want to make sure that the build is as easy for you as possible, and I also want to make it as foolproof as possible. I know many of you that have built this particular version are having some issues with the display and the thing working correctly. And that's because the build of even this device is extremely specific. All right, it's a very, very, very sensitive tool, which you'll see here in just a moment. And if the build isn't done just so, flux removed, if you're not using the proper type of flux for one, if there's moisture in the circuit, if you're using, say some offshore components that haven't been verified, things like that. There's all sorts of things that will affect the performance of this. So again, if you're building one of these things and you're having issues building this, definitely go check out the original videos again and watch them very closely. I talk a lot about this. If you build these just the way that they're supposed to be built, they turn out perfect. Again, many people here have built these things and they work just perfect. And with the original alignment procedure as well. Now, I'm about to release the specs for this thing in this video. This has never been done before, and I'm going to show you exactly how sensitive this thing is and what really makes this thing so incredibly special. The one that I'm about to release that's coming up is even more sensitive than this. Okay, so this is the tool. All right, I've put the boost circuit in here with the lithium-ion batteries and all that kind of stuff in here, and there's also the protection circuit and everything is in this box here. So this is the most current version. This has got the 29.5 volt supply and everything inside it. In order to design something like this, you need a special tool like this. Again, another thing that I've built. That is billions of ohms. So this is 0. You can look at it 0. You can use this in any way you want. So I can use this in different configurations to get different resistance values. So as you can see, that's 0, your gig ohms. So that's basically the floor where you start, right? And then the first resistor is here. It's 5 gig ohms, 10, 15, 20, and 40 billion ohms. So this isn't meg ohms. This is gig ohms. This is billions of ohms. Okay. So now in order to test this thing, and when I'm designing this thing, I need, of course, cables that are extremely, I guess you could say, low leakage. Okay, this is a Teflon cable, Teflon inserts in the connectors and everything like that. Same with these are all Teflon inserts. Okay, so what I'll do is I'll put this on the 0. All right, so put this in here like so. Try this end. And I'll put this on here, like so. Okay, so just in the center of this right now is being fed the actual voltage from the supply through the current limiting resistor, right? This is the hot lead. Here's a T, so I can measure this at the same time, and I can also attach this to this T. Okay, you'll notice that I'm on 40 billion ohms, 40 gig ohms. Okay, now it's in the forecast position. Because there's a resistor and there's a capacitor in the front end of this thing, it will take just a moment for the capacitor in the device here to charge. Okay, and that's there to keep noise and everything off the cables so that when you're testing, you don't get false readings. That was a thing that was added later on in this thing, and it's on the actual component layout sheet, and it's labeled and everything like that, but it just wasn't talked about a whole lot. I added it in the very first one, and it's because of the shielded cables, it's sketchy whether it is needed or not. I just added them just to add that extra protection. Again, a little bit of added protection is worth a lot, right? So many of you have mentioned, oh, there's an unlisted component. Well, it is on the actual component layout sheet, and it's just a simple 0.001 capacitor. Okay, so this is on the discharge position. And now we're on the test position here. Let's let this sit for just a moment. And of course, the capacitor in the tool itself is charging. Now you can see that this is sitting on the second light. It'll sit on the second or third light. Right now, this is showing leakage at 40 billion ohms. Okay, so if I remove this, I can just remove the T off here. Me touching this will even affect it. All right, remove that off. Okay. So now I'll put this back on here again. Push it down. I don't think I need to lock it. It should be okay. And we'll wait just a moment again. There you go. Again, it's indicating that we have leakage at 40 billion ohms. That's the sensitivity of this device. That's why it sees through the actual boots. All right, it sees through the actual vinyl boots. And I use this for alignment in the very first, with this particular model. Now I'm going to release a test fixture for this next one here for those of you that want to get very accurate. Now, the thing is using the boots is fine. You're going to find that you're going to get about 20 gig ohms or so, between 15 and 20 gig ohms with the boots. All right, so it's not going to be this incredibly sensitive as this right here. I've really taken the forecast right up to the top in this thing, and it tops out around 40. And after that, you really start to get a slow decline on the display. That's just because this was designed to be here. It was designed to be here, and I've just upped this to show the sensitivity right here. So very, very sensitive device. And this is the reason that any type of issue with the circuit board, even if you have a piece of FR4 board that's leaky, or it's been moist, or anything like that, when you're dealing with 40 billion ohms of leakage resistance, it's going to pretty much see that. The new one is going to be even more sensitive. Okay. Now, of course, this is the sense lead, right? And if we just me moving around by this connector, as you can see, will cause movement here. That's how sensitive this is, right? So any type of movement around this, because this is open in here, right? There's any type of movement you'll see will get reflected on that, especially at this. Now, the alignment procedure for this using a 40 gig ohm resistor is really quite simple. If you want to try doing this on yours, if your build quality is good, you'll get to 40 gigs, all right? It has to be extremely well. It'll top out at 20 quite easily. So 20 is very good, is a very, very good sensitivity for the forecast with this thing. Again, you're getting that with the boots, all right? You'll be getting that with the boots here. And the alignment procedure, I'll just go over this quickly. If you're going to actually use a resistor array, is you're going to want to align it to the fourth light. And after 10 minutes, it'll come down to the second. If you let the thing warm up for over 10 minutes, 10 to 15 minutes, you can align it to the second light on the 20 gig setting. Just because there's components in here that as they, get warm, as the unit itself gets warm, they move just a little bit. And that will cause movement in the display here. So you'll want to align it for that second light after about 10 minutes. The best thing to do is wait for the 10 minutes. The bottom line is you get just a little bit more sensitivity out of the thing when it's cold. And that's the way you can look at it. So if it's been on for a while, it'll settle right about here. Now, I've done a lot of work to this thing, and as you can see, it's really not moving. In a little while, this will pop down to the first light, and it'll stay there. Okay, so that's how it is. Again, with the 20 gig ohm setting, you want to go just a little bit higher, and it'll creep down about 2 lights after about 10 minutes or something like that. Of course, depending on the ambient temperature and things like that around. So, anyways, that is just the incurred drift in the device itself. So, of course, at 20 gig ohms, it's just going to show pure leakage. I'll just show you that right here. So, I'll just pull that off and pop this on the 20 gig ohm. And you're going to see it'll probably come up to about here. And there you go. See? So you can see 20 gig ohms, it's reflecting at this lamp right here, right? And, of course, anything lower than that, it's going to be, 15, it's going to just show right at the top, right? That, again, is in the forecast setting. So, I'll just put this back over here again. I'm going to show you what I mean about this little meter here. Okay, so we have the meter here. Now, you know what's going to happen if I try and probe this with this, right? So, the first transistor in here, right? We're going to obviously need to be referenced to ground. So, if I grab my original set of probes, bumped the mic stand there, so I'll save you from that. So everything is all attached here. Now, depending on what type of meter you have, some of them will make this go right up to the top, so show massive leakage, or others will actually just shut the transistor off. So the supplied voltage on the lead itself will shut the transistor off, and as you can see with this one here, it's shutting it off. It's making it think that there is no leakage right now. Just depends on the type of meter. Now you can see the reading that I have there. 0.01 of a volt DC. And I can keep this here for indefinitely and it won't move, right? Because really this is skewing the results. And most meters will do this. So it's one way or the other. So, 40 gig ohms is much, much higher than the factory. Just move this cable here. Much higher than the factory specs for the input resistance on any of these types of meters, right? So what I'll do is I'll just plug in this probe here again and turn on the power supply. So I need to just ground this to here. Same way I did that, I'll just clip it to this switch. It'll be fine. Turn on the power supply and it's on. So if I ground this out, you'll see, there we go. Looking good. So now what I'm going to do is, now keep in mind that there's a filter in here. A capacitor has to charge in here as well. So you'll see this get dragged off for a second, but you'll see it come right to the same light again. So here we go. Again, that capacitor was put in there just for reasons of keeping noise down on the actual probe. And there you have it, right up to that second light, just like before. And that's the actual reading of the voltage at the base of the very first transistor. So it's not right at the base, it's 20 megs in front of it, right? Isolated by that first resistor, but that's what's actually there right now. 0.866 of a volt, and as you can see, it's moving just a little bit. Now, the reason that you find that moving is that's that incurred drift inside, and that's actually caused by the forecast floor setting transistor. So that little bit of movement is just due to temperature variation inside there, and as you can see, it's the extreme digit right over there to the right-hand side. So it'll move for a while, right? But it eventually will stable off. So there you have it. Now that it's charged, you can see I can go and measure it. And as you can see, there's like no effect. Right? And that's what's needed to work on a device like this when you're designing it. So you can't have the test equipment drag what you're working on. Again, the test equipment needs to remain invisible to what you're working on. So your test equipment, the device under test, cannot see the test equipment at all. If it does, then of course, I'll just ground this out again. You get effects like this from a standard meter, right? It would just drain it right off, right? So again, this will just charge the filter inside this probe, and we'll be off to that second light here in a moment. There it is, and we start getting our readings back. It would be much, much faster if I didn't have the filter in here, but everything's about balance, right? So I wanted that filter in there just to keep things as clean as possible. So there you have it. That's probing right on top of 40 billion ohms and not affecting the reading at all. Very, very, very sensitive device. So what I'll do is I'll get this all out of the way and I'll show you inside the probe here. All right, let's take a look inside the probe. Screw out there. Actually, what I'll do is I'll remove this as well. A wire under there that needs to come out. Move that off to the side. Let's remove the tip. Like so. And you can see in there, so there's a spacer and a washer. You can see that there's just a rubber grommet, so I use that just to put on top of the board to hold the board nice and tight inside there. That's just sitting on. No, this is not vinyl. So, okay, little screw stuck there. Remove that. So now you'll see a piece of braid that's off to the side here. That's to make contact from the ground to the shell, to make sure that the shell is grounded so that I don't add noise into the circuit. That's very important. That's just a piece of folded braid. There's a cardboard protective tubing right here. This came with the factory probe. So I just take that off. And that is what is inside. So I'll just take down the exposure here just a little bit. And that'll probably help out. So you can see that's what it is. It's a Motorola part. Not a whole lot to it. An IC in there. Some filtering at the top on the rails. This is the input. That's the input filter there. So the input comes in here through a 100k ohm resistor. There's a filter to ground, and then it goes through another 100k ohm resistor right directly into the IC. And then there's some resistors on the out to just basically stop any effects on the IC from cable capacitance and things like that. And then, yeah, it's pretty much it. Nothing on the other side, just like so. Now the new one, the new design will be something like this. It'll have an IC. This is a through-hole part that I've just mounted on here. So I played with a whole bunch of parts just to optimize things, right? And of course I made sure that the circuit board would fit in here like so, and then this would go on, and everything went together just like so, nice and safe, so that nothing would, touch the shell here. Now this came with the factory probe. This came inside this thing as it is, so that made things nice and easy there. So just a little bit of measurement. Now you'll notice that this is surprisingly like the super probe. So basically what I did is I used the super probe size right here, right? So I just cleaned off everything that was on the super probe and then started with a new layout, just leaving this here and then adding a single inline row, like a single inline pin row at the top here, and then just put new components on it like so. So started fresh there. So, and that's what it is. Right there, that is the part. So I just bypass caps and everything. So when I get the next one built, which will be released with the next capacitor tester, so you guys can do some further testing and things like that, I'll release, a schematic and a layout with it as well. So I'll also release the very, very low current reading probe. I guess you could look at it like that. That's all it is. There it is. So I hope you enjoyed. The new capacitor tester is coming soon. Again, working day and night on the thing, as well as doing everything else that life requires at this time. So if you enjoyed this video, you can let me know by tapping the heart symbol just below the comment section of this video here on Patreon. And I will talk to all of you very, very soon with a very neat new tester coming. Bye for now.